Good morning, my dear. Today we have a session with a new technique in testing the hypothesis. Hope you all remember the different statistical tests you have learned like Z-test, T-test, F-test and all. Then why do we need another test? For that, you just imagine a situation where you have started a small textile shop where you have just two salesmen. And by the end of the year, you want to evaluate the performances of the two salesmen, whether they are performing equally or not. So which test you can apply here? Obviously T-test for two samples since you have two salesmen. But my question is, suppose you have one more salesman, your shop is little more developed and you have three salesmen. Then how can you evaluate the performances of three salesmen by the end of that year? So here if you prefer T-test, what you can do is either you can take conduct the test between the first two salesmen, that is salesman 1 and 2. Since in T-test we can take maximum 2 samples at a time. So you can carry out T-test for the first and second salesman, then again T-test for second and third salesman, then again T-test for the first and third salesman. So here you have to carry out this T-test 3 times. Okay, so each time when you carry out the test, remember 5% level of significance is there. That is, we are expecting the probability for type 1 error to happen 5% every time when we conduct the t-test. So when you do it 3 times, that error also increases and it is time consuming and your effort also increases. Okay, so here we need another test which reduces our effort and also it reduces the probability of error also. So here we have the new technique, analysis of variance. Analysis of variance is abbreviated as Anova, and it's a technique which is introduced by Sir Ronald Fisher. The one behind this technique is Sir Ronald Fisher. Now let's see what is Anova and how to carry out the test, what are the procedures for it. And also I'll show you an illustration for the same. Now let's see some slides regarding the definition and the different categories and the procedure for Anova. So here you have the definition for Anova. Analysis of variance is a technique which analyzes the variances of 3 or more samples for determining the significance of difference in the sample means and for determining whether the samples are taken from same population or not with the help of F-test. See, here we have this technique analyzes the variances of 3 or more samples. Variances of the samples. In order to find the difference between the sample means, here we are analyzing the variances. So in this test, that analyzation of variance is involved. So this is conducted with the help of F-test. F-test, you know, it is the variance ratio test. So Anova is conducted with the help of F-test. Here the test statistic is F. Next, one-way Anova. See, if the observation, Anova basically of different type, one-way Anova, two-way Anova and multi-way Anova. If the observations are grouped classified into groups on the basis of a single criterion, then it is called a one-way Anova. If the observations are classified into groups on the basis of a single criterion, it is one-way Anova. So obviously if you have two criterion, it is two-way Anova. Now let's see the procedure for one-way Anova. Before moving to the procedure, as I have told you, this is a test where we are analyzing the variances. So here we have different variances involved in one-way Anova. And those variances are, you have 3 variances. One is the variance between sample and another is variance within sample and another is the variance among the sample. I repeat, we have variance between the sample, variance within the sample and also variance among the sample. With the help of it only we can conduct this procedure and carry out the Anova. Okay, as in all statistical tests we have a common procedure. All the statistical tests begin with an assumption. So we have to set the hypothesis first, then we have to compute the test statistic and then we have to determine the table value. For that with the help of alpha and the degree of freedom we can find the table value. Then we can arrive at a conclusion comparing the test statistic with the table value. If the calculated value is less than the table value, we can accept the hypothesis or else we will reject it. This is the common procedure for all statistical tests. But here in Anova, the procedure is same, but in order to compute the test statistic, we have to do a little more. That I will show you. First we have H naught. H naught. Now let's see the procedure for Anova. First we have H naught. There is no significance of difference in the sample means. Why? Because we are testing the different sample means. So you can either put all means are equal, or else you can write there is no difference in the sample means. Then next we have to compute test statistic. As I have told here, we have the test statistic F. F is the ratio MSC divided by MSE. MSC is read as mean square between sample, and MSE is mean square within sample. So the C is for between sample and E is for within sample. I've told you we have three variances in one way Anova: variance between sample, variance within sample, and variance among sample. Among sample is actually the total. So here we have mean square between sample and mean square within sample. So these two terms we have to calculate. For calculating that, we have several steps. That is, I'll introduce you several terms. First is T. Before that we have N also. N, as you know, N is the number of observations. N is the number of observations, and one more letter K. K is the number of columns. K is the number of columns. Okay, you can count the number of columns, but this K is different in different textbooks. Sometimes you can use, some people are using C for that, and some are using K. So here I have taken it as K. Then next to T. T is the sum of all observations. T for total, like that you can think, T for total. T is the sum of all observations. Then SST, sum of squares between the sample. Next we have SST. SST is the sum of squares of all observations minus T square by N. I repeat, sum of squares of all observations minus T square by N. So you have to find the square of each of the given observations, then we have to find the sum of it, then from that you have to subtract T square by N. The next is SSC. SSC is the sum of squares. C for between sample, I have told you, C for between sample. So sum of squares between sample. Okay. Then this is equal to sigma x1 by n1 plus sigma x2 by n2. Sorry, you have to square it. Sigma x1 square by n1 plus sigma x2 square by n2 plus sigma x3 square by n3, etc. minus T square by N. For each of these terms, sigma x1, sigma x2, sigma x3, etc. represent the total of each column. So you have to find the total of each of the columns, then you have to square it, and that divided by n1, n2, n3 respectively. That is the number of items in each columns, number of items in the respective columns, and that minus T square by N. Then the next step is SSC. SSC is the difference between SST and SSC. SSE equal to, that is sum of squares within sample. It's read as sum of squares within sample. That is equal to SST minus SSC. Now I will give you a tip to remember this. Actually this SSC is the sum of squares between sample. So C for between sample and E for within sample and T for the total. Okay, but you can remember in this way that C for column, T for total, and E for the difference between T and C. Okay, C for column, T for the total, and E is the difference between these two. Actually this is not the definition. The definition is C for between sample, E for within sample, and T is the total itself, among sample or total. Okay, then next is MSC. We are computing all this for finding the value of MSC and MSE. Now we have calculated the rest, so you can find MSC and MSE. MSC, it is the mean square between sample. Mean square between sample. So there we have the formula SSC divided by K minus 1. SSC we have already computed, then K minus 1. K is the number of column, so number of column minus 1. The next is MSE. MSE is equal to SSE divided by N minus K. SSE divided by N minus K, where N is the number of observation and K is the column number, and the numerator SSC we have already calculated in the fourth step. Okay, so in this way we can calculate the two terms for the F ratio, MSC and mean square between sample and mean square within sample. Once we got it, we can put it in the F ratio. F ratio for the Anova test is one-way ANOVA test is MSC divided by MSE. Also remember, in F test always we will put the greater number in the numerator. So after finding MSC and MSE, you have to compare both, and the number which is greater in magnitude will be in the numerator. Then next is degree of freedom. In order to find the table value, we have to take the degrees of freedom. Then in 5% alpha, you can take the table value. So here the degree of freedom is k minus 1, n minus k. See, these terms are the denominators you have seen in the 5th and 6th step. MSC is equal to SSC by k minus 1. There you have this term k minus 1, and in next term you have n minus k. So these two denominators are the degrees of freedom. So degree of freedom here is k minus 1, n minus k. Corresponding to these two degrees of freedoms from the statistical table for F, you can take the degrees of freedom. With that, you can find table value. Using this 2 degrees of freedom, you can take the table value. And next step, we have to derive the conclusion. Comparing the test statistic with the table value, we can arrive at the conclusion. Like if the test statistic is less than the table value, we can accept the hypothesis, or else we will reject it. Next, let's see that illustration. I've given you a problem in the beginning. Let's see the problem once again. Then I'll show it and I'll solve it for you. Now let's see the question. A tea company appoints 4 salesmen A, B, C, D and observes their sales in 3 seasons. The figures are given in the following table. So you can see salesmen, the sales carried out by the first salesman, then second, third, fourth. We have 4 people here, and the question is, do the salesmen differ significantly in their performance? So we have to evaluate the performances of the 4 salesmen. So here we can carry out one-way ANOVA since the observations are categorized on the basis of a single criterion. Now I will show you how to carry out this one-way ANOVA. Here we have the problem. I just have written the numbers. We have the 4 salesmen A, B, C, D, and these were the sales given. Okay, and now see the numbers are 2-digit numbers. So when you are squaring and then you are adding it, you will get bigger numbers. So in order to make the calculation little more easy, I have just taken a deviation of all numbers from a particular number. So this is not a this step is not must. If you are using calculators, you can do the steps directly. I am taking deviation. Why? Because so that I can get smaller numbers. And for taking deviation, there is no issues. Why? Because in ANOVA, you know, the final product is our F test, F ratio. So since it is ratio, it is dimensionless. So if you are taking deviation using any number, that is you can do addition, subtraction, multiplication, division, or any fundamental operations with any numbers, with any constant number, a common factor, there will be no change in the result. You need not to make any subsequent changes with the result. You will get the correct result. And number, you can choose any number of year on. Here I have taken 29 only because I just have tried with the 30, then more decimals are coming. That is why I have taken 29. Since 29 you can see 3 times repeats. So when you take the deviation, you will get 0. Therefore your calculation part will be more easy. That is why I have taken 29. X minus 29. Now we have subtracted each number minus 29. That is 36 minus 29, 7. 36 minus 29, 7, like that. The numbers are written here, and this is the total of each column. Since we need the total, I have just added the total. You can see 7 minus 1 minus 3, you will get 3. Like that, the total is also written here. Next, we have to start the test. First step is to set the hypothesis. So I am writing H naught. H naught, as you know, all means are equal. You can take the performances of all salesmen are equal. That is our assumption. So I am writing all means are equal. Then next, we have to compute the number of items, count the number of items. N equal to, how many item observations are here? We have 4 columns, 3 rows, so we have 12 items. Then next, how many columns we have? We have K equal to 1, 2, 3, 4 columns are there. And then next, T. T is the sum of all observations. Sum of all observations. So 7 plus etc. up to 0, you have to add the entire all observations. That is, the sum is here actually. You can add this, get cancelled, 9 plus 3. 12 is the total. Whole total is 12 here. Then you can compute T square by N. T square by n is equal to 12 square, we have 144 divided by n again 12. So 144 by 12 we will get 12 again. Okay. The next we have to compute SST, sum of squares of all observation minus t square by n. You can go to the procedure and see the formula. SST is equal to sum of squares of all observation minus t square by n. So we have to square each of these items. Now I am doing with this only. This you need not to look into this. This with these numbers we are doing the test. So here squares of each observation. That is, you have to take the square of each of the numbers, 49 plus, then minus 8 square we have 64, plus we have 36, plus 1 plus 0 square is 0, then 2 square is 4, then 3 square 9, then plus again 3 square 9, plus minus 1 square is 1, plus 0. Now this minus t square by n. T square by n we have already calculated, t square by n is 12. So this is equal to, now we can add it. I didn't do anything much more. As you see, I just have taken the squares of all the numbers. Simply take the square of each of the numbers, then you have to find the sum of it, and that minus t square by n. This is our formula. So this is equal to, now we can sum up the terms, 49. So we have 98 and this is 100, then plus 2, so we have 200, plus 9 plus 4, 9 plus 4, so we have plus 22, 222, then minus 12. So here we will get a sum of 210. Therefore, SST is equal to sum of squares of all observation minus t square by n, that is 210. Next step we have SSC, that is sum of squares between the sample. Okay, remember C4 column. So here we have to take each column total and then we have to square it. The formula is sigma x1 square by n1 plus sigma x2 square by n2 plus sigma x3. How many columns you have, that many number of times you have to do it, minus t square by n. So here the first column total is 3. So 3 square, that is 9, by number of items in the first column. Number of items in the first column is 1, 2, 3. So we have 3 plus again second column total. Second column total here we have 6. So 6 square is 36 divided by again number of items in each column. Here in this problem we have same number of items. So in each column we have 3 numbers. Then plus next column total is minus 6. Squaring it you will get 36 divided by 3 again, plus then fourth column 9. So squaring it you will get 81 divided by 3. Then so that total is over. Then minus t square by n. T square by n we have 12. So now this is equal to 36 plus 36 you will get 72 plus you have 90. So you will get 162 divided by 3 minus 12. So we have 54 minus 12, that is we have 42. Next SST we got, SSC we got. Next we need to find SSE. Hope you remember the formulas we have discussed. T for total, C for column, and D is the difference between the two. So now we can take the difference between these two, 210 minus 42. You will get 168. So now we got the 3 terms. Next you can compute the mean square between sample as well as mean square within sample. So mean square between sample MSC is equal to, by formula we have SSC divided by K minus 1. Sum of squares between sample divided by column minus 1. This is the formula. On substituting the values in this formula we have SSC is 42 divided by K minus 1. K minus 1 is column minus 1. We have 4 columns here for the 4 salesmen. We have 1, 2, 3, 4 columns. 4 minus 1 is 3. So 42 divided by 3, you will have 14. The next MSE. MSE is the mean square within sample. So here we have the formula SSE divided by n minus k. SSE divided by n minus k. So here you will get SSC I have already calculated as it as 168. Now n minus k, see n is equal to 12, k equal to 4. So 12 minus 4 we have 8. So this is equal to, and cancelling you will get 2, 1. MSE is equal to 21. So we have done with the MSC and MSE. Next we can find the F ratio. We have done all this to compute the test statistic. So here we have the F ratio. F is equal to MSC by MSE greater in the numerator. Check the two numbers 14 and 21. 21 is a big number. So 21 divided by 14. Thus you can cancel with 7. So you will get 3 by 2, that is 1.5. So we have that F ratio 1.5. Okay. Now only that table value part is remaining. We are about to finish. In order to get the table value, we have to take the degrees of freedom. Degrees of freedom here for one-way ANOVA, I have told you we have k minus 1 and n minus k is the degrees of freedom for one-way ANOVA. That is these two denominators k minus 1 and n minus k. What are those numbers? 3 and 8. 3 and 8. Or else you can check k minus 1, 4 minus 1, 3, then 12 minus 4, 8. So anyway you can write 3, 8. Now you have to find the value from the statistical table corresponding to alpha 0.05 and degree of freedom 38. You can write the table value. Okay. Hope you will have the statistical table with you. Here I am giving you the number. Here the number is 4.07 is the table value. We can take 3 in the row of the statistical table and 8 in the column of the table. Then corresponding to that 3 and 8 you will get 4.07. Now we got the test statistic 1.5 and the table value 4.07. Comparing these two, you can see this 1.5 is less than 4.07. That is here this test statistic F value is less than the table value. So here your conclusion is accept H naught. Accept H naught. That is our H naught was all means are equal. So here the conclusion is all the 4 salesmen perform equally. Their means are similar. Okay, I'll explain once again. First we have these numbers, and since the numbers are little big, I've just taken deviation from a number 29 and I reduce the numbers in magnitude. And this method of reducing the magnitude of numbers is called coding. Coding method. Coding method is the method there we are reducing the magnitude of the numbers by a constant, any number. Okay, so we have reduced the numbers and these are the numbers, these are the column totals. Then we said the hypothesis that all means are equal. Then we have counted the numbers n, k and t is the total of all observation. Then we find this t square by n. Then SST, sum of squares of all observation minus t square by n. So we have taken the squares of each of these observations and we find the total of that, and that minus this t square by n, we got 210. The next SSC is the sum of squares of each of the SSC is each column total, we have to square it and divided by number of items in the respective columns. So we have the formula sigma x1 square by n1 plus sigma x2 square by n2 plus etc. minus t square by n. So I have taken the square of each of the columns and divided by each of the column totals and divided by number of items in all the columns. Here it's same number 3 and minus 12 we got 42. Then SSE is equal to difference between these two. So we got 168. Again we have computed MSC and MSE. This is for finding the F ratio. Using these formulas, we have computed MSC and MSE and we got the F ratio as 1.5. Remember, when you are finding the F ratio, you have to compute it like greater by smaller. So we got the ratio as 1.5. Then next we have to find the table value. For that you have to find the degrees of freedom. Degree of freedom for one-way ANOVA is k minus 1 and n minus k. So corresponding to 3 and 8 from the table F table with the 0.05 level of significance, you can see table value is 4.07. Check your statistical table and check the value, you will get 4.07. Then comparing these two, your computed value is 1.5, the F value is 1.5 and the table value is 4.07. So the computed value is smaller than the table value. Therefore, we accept H naught. This is our conclusion. So here we got the means of all samples are equal. That is, our conclusion is all salesmen perform equally. Okay. So here we are done with one-way ANOVA. Hope it's clear. Now I am giving you another question. See, this was the question we have solved just now. Here we have 4 salesmen and the question was whether their performance difference, the significant difference is there in the performance of the 4 salesmen. Then next I am making a small change with the question and you have the next question. See, this is the same data, same question and the first part we have solved, and here in addition to this first question I have added one more question, that is there significant difference between the season? Then left side you can see the 3 seasons are mentioned. So here I want to analyze the performances of the salesmen as well as the effect of seasons on the sales. Okay. So one question is whether the performances of the salesmen are different. The second question is the seasons, influence of the seasons on the sales. So we have to do 2 categories are here. So we have to carry out two-way analysis of variance. That is, here we have 2 categories. Observations are classified on the basis of 2 criterions. One is the salesman and another is the season. So you have to carry out two-way ANOVA. With that, let's see next time. Thank you.